In this video, we're going to be discussing Introduction to Mass Spectrometry, and we're going to continue on the topic of determination of empirical formula, part 2. Remember in the last video, we had been talking about how to use the C13 peak to determine the number of carbons in the empirical formula of a compound based on the mass spectrum. If you look at the molecular weight and you look at the M+1 peak, you can determine how many carbons, because each carbon will create a naturally occurring isotope, which is unavoidable, of 1.1%. We can look at other elements as well as carbon, because elements contain naturally occurring amounts of isotopes. If we look at this table, carbon-12 is the most common abundant isotope of carbon, with carbon-13 showing up at 1.1%. That makes this an A+1 type element, meaning that when you see it in a spectrum, its isotope will show up at the molecular weight +1. So carbon-12 will be the most common. Carbon-13 will show up at 1.1% for every carbon that is there. Oxygen, its most common isotope is 16. It shows up most of the time. And oxygen 17 typically doesn't show up. Oxygen's most common isotope is actually oxygen 18, which only shows up at 0.2%, meaning it is an A+2. Sulfur is also considered an A+2, but has isotopes both at S33 and S34. We can use this information given in this table to determine empirical formulas beyond just hydrocarbons. Let's look at this example. Here is a mass spectrum. These are the peaks which are generated from these mass intensities. This is simply a tabular form of the peaks that you see in the spectrum. If we look at this mass spectrum, the first thing we will notice is that the molecular weight equals 72. So its mass of all of the most naturally occurring isotopes will be 72. If we look at its molecular ion region, we see isotopes of A+1 at 3.5% and A+2 at 0.5%. This means that these isotopes are coming about from whatever elements exist in this molecule. Right off the bat, the A+1 of 3.5% might mean to you that we're looking at 3 carbons. And since we're dealing with hydrogens, well, we probably have some, but we don't know how many. The question is, what elements could create an A+2 of 0.5%? If we go up and we look at this table, we can see that all of these different elements can add up to different isotopic distributions. If we had, for example, a chlorine in there, we would expect to see an A+2 of 32%. And there certainly is no peak there representing chlorine. So we can be sure that chlorine doesn't exist, sulfur doesn't exist, bromine doesn't exist. But of the something that has to be creating an A+2, we see oxygen will actually create an A plus 2 of 0.2%. We need to get to a molecular weight of 72. 3 carbons will get us 3 times 12, or 36. We have some hydrogens. If there were oxygens there, that would give us an A plus 2 peak. In fact, if each oxygen were to give us a 0.2%, it might make sense that the A plus 2 for 2 oxygens would get us to 0.4 or perhaps 0.5%. This means that these isotopic distributions are consistent with something that might have 2 oxygens. From this mass intensity, we can guess that we have 3 carbons, 2 oxygens. That would be 36 and 32 of the weights. We'd have to add up 4 more to make our 72. We can deduce that the empirical formula of this compound, given this isotopic distribution, has an empirical formula of C3H4O2. We can continue this by looking at additional problems. In this problem, a somewhat smaller molecule for a simpler example, we have a total molecular weight of 26. We have an M plus 1 at 27 of 2.2%. Of the only rational explanations that can come about that would make that isotopic peak occur, that would suggest 2 carbons. That would get us to 24 of the AMUs. 2 hydrogens would make this molecule acetylene, C2H2. Continuing on, this has a molecular weight of 27. That should immediately mean something to you. It has an odd molecular weight, which means it must contain nitrogen. If the nitrogen shows up, then the 28 peak at 1.6% might mean that we have 1 carbon 12. If we go back and look, nitrogen is going to have a molecular weight of 14 normally, and an A plus 1 of an additional 0.3 or 0.4%. That means the C13 peak could be 1.1%, and the N15 peak could be about 0.4%. That peak at 28 could come about from 2 different sources. C13-1, N14, H1, or C12, N15, H1. That peak is a combination of the 2 different isotopes that add up nominally to 28. Both of these isotopic empirical formulas create a total peak of 1.6%. The empirical formula, of course, is HCN. Sometimes the lack of isotopic information can also give us indications of the empirical formula. Seen in this example, we have a peak at 34, which is the intact molecule. Our A+1 peak, or our isotope peak, at 35 is 1.1%. Well, that's pretty clearly a case for the only thing that's going to make a M+1 peak at 1.1% is one carbon. So if we have one carbon and we have some hydrogens, we just have to come up with what is going to get us to a total weight of 34. I guess we could do 33 hydrogens, but you're going to have a heck of a time writing an empirical formula or a Lewis structure for that. So what other elements could be in there? Clearly, there's not a nitrogen and there's not an oxygen because I don't see an A+2 peak. I don't see any of these isotopes. I only see the carbon-13 isotope. But some of these elements are A-type only elements, meaning they don't have naturally occurring isotopes. One of them is fluorine. Fluorine shows up at a mass of 19 with no other isotopic labels occurring. The fact that we don't see any other isotopic information suggests that there has to be additional mass being added by A-type atoms, or things that don't add additional isotopic information. If fluorine were 19, then we could deduce that the empirical formula would be C1H3F1. The only isotope that would show up would be the C13 peak at 1.1%. The total mass would be 34.